Swayam Prabha. Digital India. Educated India.
So, we will continue the discussion on kinetic Monte Carlo simulation of continuous Markov process. So, what we are talking about here is there are some continuous Markov process for which there may not be a analytical solution. So, what you could do is then create a very large number of trajectories or sample paths that characterizes the continuous Markov process, and then from these large number of samples you can extract statistical quantities of the process. Okay. So, you can think of kinetic Monte Carlo method as a numerical way of solving the Fokker-Planck equation representing continuous Markov process. As we know that for any continuous Markov process we have to identify the two characteristic functions that means the drift and the diffusion. Okay. So, this is more like a deterministic part and this is the stochastic part, and of course, you also need an initial condition. Okay. As with any other dynamic process, you have to know what is the initial condition for the given process. So, once we have all this information, then we can set about the conducting a kinetic Monte Carlo simulation to generate sample paths. So, let us talk about a pseudo algorithm. In step 1 is initialization. Okay, you will say you will specify x naught at time t naught, okay, and then also specify all the functions. Step 2, we have to choose a time step, choose a suitable time step. Delta t. Okay. Then step 3, you will generate unit normal random variable. Okay. Step 4 is where you will update the position x at d plus delta t, okay, is equal to x of t plus a of x comma t times delta t plus square root of b of x comma t delta t, then you have n of 0 1, and then you will actually be looping here. Once you update this, you will go back, choose another delta t. Sometimes we will see that the delta t need not be constant always, it may change in between. So, or if delta t is chosen to be constant, so you will be only looping between here to here. Okay. So, when you loop here, you will be basically generating x of t versus t. Okay. You can also update time here, t is equal to t plus delta t. Okay, so if you update time t at every time step, you are basically generating sample paths x of t as a function of t. Okay, so this is a kind of, yeah. What is the? Not audible. In what case? Okay, I am going to talk about that. Okay, so I was going to say that there are two decisions have to be made. One is how to generate unit normal random variate. We already have discussed, but anyway I will give you the equations. That's the easy part. This choosing this suitable time is something that needs some sort of consideration, because the choice of delta t also depends what is the nature of these functions, whether they are constant, whether they time vary, or whether they depend on the current state. So depending upon those case, we have certain conditions to be followed, okay, in choosing time. Okay, in fact today's discussion is all about that. Okay, okay, so just set the stage. These are the kind of regardless of what kind of continuous Markov processes, you are going to follow this kind of an outflow, right? Define the characteristic functions, initial conditions, and then you can write any sort of programming using any programming language. You can write a very simple code, initialization, choosing a time step based on some condition I am going to discuss, generating random number, and then updating the current state based on the old state, and then you loop over this. Once you exit from here, then you have generated trajectory 1. You can put another loop over this to create many such trajectories. Okay, you can have another loop above this where you can create many such trajectories, and then for each of those trajectories you can estimate properties. Okay, so now if you ask me, okay, how did we do this? Okay, so we talked about a Box-Miller method. So so this is to generate a unit normal random variable. Okay, so here what we do first is to generate, we will generate two uniformly distributed random variable, u1 and u2. Okay, so u1 and u2 are uniformly distributed random number in the limit 0 to 1. To generate these, you can use this congruential methods, mixed congruential method, multiplicative methods, etc. Again, we saw those things in the very beginning of the course. Okay, and then what you do after this is you say that n1. So based on these two, we can actually generate a pair of normal random variate. So this goes as something like 2 ln 1 by u1 cos 2 pi u2, and n2 so the two uniformly distributed random number u1 and u2 are used to calculate or to generate two unit normal random variate. So you have the prefactor square root of 2 ln 1 by u1 and then cos of 2 pi u2. So this u1 and u2 are the one that you generate here. Okay, this one will give you one normal random variable, and the sine function will give another one. So you basically in one step you can create two uniformly distributed random number. Okay, so that takes care of this step. Okay, so that means when you are in this stage, you would actually write a small subroutine or a function that will call this function and get two random numbers normally distributed. Clear? So now comes this second issue, that how do we choose a small time step, okay, a suitable time step. So here what we need to think about is for any numerical algorithm, we think about accuracy and we think about speed of computation. Okay, for example, in the context of solving a deterministic equations, okay, differential equations using Euler's method, Runge-Kutta method, Adam-Bischoff method, etc., etc. So here we say, okay, you know, I want to have delta t small enough so that I get accurate results, but at the same time delta t should be large enough that I can achieve my computation over a reasonable amount of computing power. So there's always a trade-off between accuracy and the speed, right? You can take a very small delta t and get a very accurate result, but then it could be very expensive computationally. On the other hand, you can choose a very large delta t, get your computation done very quickly, but you are going to lose accuracy. So there's always this trade-off. The same issue comes here also. In solving this kinetic Monte Carlo simulation, in the choice of delta t also brings the same issue. When I bring this delta t very small, of course I can get very accurate results, and then when I have a large delta t, then I can actually save time. Okay, so you would be thinking about how large delta t I can choose. Okay, that's our aim. So now we want to choose delta t large enough such that we do not violate the Markov property. Okay, by choosing a larger and larger delta t, you are actually violating the Chapman-Kolmogorov condition, which is basically underlying the property of a Markov process. So that's where the loss of accuracy comes in, and you don't want to do that. But you can choose always a smaller delta t, but then again, are you willing to pay the price, computation price? Okay, so those are the two issues. Okay, so now what I'll do is I'll go back to that condition where exactly we are violating the Chapman-Kolmogorov equation or the Chapman-Kolmogorov condition which underlies the Markov property, and how we can choose delta t so that we don't compromise on the accuracy. Okay, so what I'm this is an equation that I have not derived in the class, but I'm only using this equation just to justify the choice of delta t. So what I showed in the previous class was only this part. Right, that's exactly what I'm using to update my next position or next state of the random variable. What I'm neglecting is this additional term, which I call it as an error term. Okay, just like when you try to discretize a differential equation, you have the linear order, the leading order terms, and then you have the higher order terms, which we generally neglect by saying that at a small delta t, those higher order terms can be neglected. Okay, so then the accuracy of those numerical method depends on the order of which up to which we are actually neglecting. Okay, higher order terms are typically neglected. We keep only the leading order term. So the accuracy basically means when we choose a very small or very large delta t, how much of this is going to contribute or how much are we actually neglecting, that is what actually gives rise to the accumulation of error. Okay, so that's where we deviate from accuracy. So here we have a very similar situation, that we take only this leading order term in updating the state of the system, and we are leaving behind a correction term. Okay, so now when I choose a very large delta t because I want to save computation time, we have to basically assess the weight of this term versus the actual leading order term. Okay, so we want to choose a delta t such a way that this term is small compared to these leading order terms. Okay, so that's the criteria. If I choose a very small delta t, this will anyway will drop out, I can get a very accurate result, no problem. But my ambition here is to choose a big enough delta t, large enough delta t, so I can do my computation faster. At the same time, I don't want this term to be dominant with respect to the leading order term. Okay, so that's basically going to put you some sort of, we want to basically look at the ratio of this term over this term, and that term should be very small number, some small epsilon, 0.1, 0.01, etc., etc. Okay, so that is going to be our condition. So therefore, we take the ratio of these two terms. This n1 here and n2, these are all again unit normal random variables. So this has to be a very small number, epsilon. Okay, this ratio of the error term by the leading order term, that should be a very small number. Okay, so we can also remove all these random variables n1s and n2s, so that they don't really factor in the condition of the choice. So from here, what we can say is that, okay, there is some prefactor. Of course, it depends on the characteristic functions a's and b's, so basically that means this condition is going to be dependent on what are my choices of a and b, whether they are constant, whether they are functions of x. If they are functions of x, is it linear, non-linear, etc., etc. Okay, so it very much depend on the characteristic functions. So here what we can say is that you have certain number, and then this is multiplying this whole thing, and then divided by some number is less than 1 or less than some small number. So that means this entire quantity here, that has to be less than 1, right? Because if this is much higher than 1, then this condition may not be possible. Okay, so we say that whatever is multiplying here, one of the criteria is that this has to be of the order of 1 or much less than 1. Okay, so we say that the square root of the derivative of b dou x delta t plus this has to be a very small number itself. So from this condition, we are bringing even more stricter condition that this entire term has to be a small number itself. So now we got two terms, and what we can do is we can actually define delta t from each of these terms. Suppose if you have only this term, you can choose what should be the delta t. If you have only this term, you can see what is the smallest delta t. Then we can choose the delta t minimum of those two. Okay, so that we take care of both conditions. Suppose if you take only this, this is 1 and the other one is So, I am separating that simultaneously, that this has to be small. So, this will give me a delta t that is epsilon by dou a by dou x. Of course, you have to take the modulus of this, take the absolute value of the derivative, and then if I bring this one, so by looking at these two, we want the delta t to be a minimum of the two conditions. Okay. So, what we have done here is we have said that this term that we have in this bracket has to be a very small number, epsilon, and then we are saying that individually these quantities have to be less than some small number epsilon. So, I am taking the first condition here, and from here I can choose my delta t such a way that it has to be less than some epsilon square by the derivative dou by dou x of square root of b whole square. Okay. Similarly, from the other condition, delta t has to be smaller than some number by the gradient of a. So, finally, this is the condition that we want to be satisfied. Okay, and we say this is the condition for accuracy. If we do not enforce this, if we arbitrarily take a delta t large values, we may accumulate some error because of this term, and that will actually compromise the accuracy. Okay. But by ensuring that delta t is chosen based on this condition, we always say that this quantity is going to be much smaller compared to the main leading order term, so that you are not compromising on the accuracy. Okay. So, now coming back to this algorithm, when I say choose a suitable time delta t, this is what I meant. Okay. So, if your a and b are functions of x, your delta t may also change with respect to time, because the state variable x is also changing. If a and b are constant, then you can have a case where delta t may not change all the time. So, you are either of this case. So, either delta t can change during the simulation run, or it can remain constant. It all depends on the choice of a and b. Any question here? Now, what we can do is we can take some example problems that we have seen before, and we can see under what condition delta t is constant, or going to change, etc., etc. Let us say you want to simulate a Wiener process, which is characterized by a of x as constant, and b of x comma t also is constant. Okay, it can be like 0 and 1, or it can be having 0 and 2d, etc., etc. Okay, so this is one condition. So clearly, now if you apply this condition, what happens is, in this case, dou a by dou x, x is the state variable here. Okay, so this is 0. right? And similarly, the other derivative, this also is 0. So then, regardless of the epsilon that I choose, you have basically infinity here and infinity here. That means delta t can be as big as you want. Okay, there is no really you are not losing any accuracy by choosing a large delta t. Okay, so delta t can be minimum of. Okay, so you will get exact result for any choice of delta t for this particular case. But in this case, of course, you want to take, you can take any delta t you want, but then if you take a very long delta t, what will happen is you will not see the stochastic fluctuation of the process, okay, because you may have just only few random points, few points for the entire simulation, okay, and then you may not actually see the entire stochastic fluctuation of this problem, okay. So now we can actually bring another condition for this kind of cases, what I call the plotting condition. That is, when you plot the sample path, you want the sample path to represent the true dynamics of the system, showing the drift, showing the fluctuations, stochastic fluctuations that is inherent. Okay, for that you could actually say I will overlay another condition so that my data are grainy enough that I can see all the local fluctuations. So that is called the plotting condition, which is more valid for only these kind of cases where the accuracy condition does not impose any choice. Okay, so in this case I can say so this has to be chosen, delta t is to be chosen such that stochastic fluctuations are visible. When I say visible, I mean when I plot it, this basically I meant discernible. It should be something that has to come apparent over deterministic quantities, deterministic variations. Okay, so that's going to give us a plotting condition. So what I actually mean is this: when I update, I choose a delta t, big, small, whatever it is. I am updating the state variable here. So this is the drift term or a deterministic term, and this is the stochastic term, right? So I want this to be dominant, than this one, so that I can see all the fluctuations. Okay, so all I am saying is take the ratio of these two terms, and that's going to set a time scale for the delta t. Okay, so we can say that square root of b delta t over a delta t has to be some small number epsilon, right? should be opposite. Yeah. Diffusion should be yeah, that's what I wanted to say. Let me just see if I want this to be so why do you say this has to be the opposite? Right. So now actually what I have done here is I have assumed that this fluctuation is smaller than this, because this number is very small. So this condition is saying that this has to be much smaller than the drift. That is not the condition I want. Actually I want the other way around. You are right. Okay. So I should have written this as A delta t over square root of B delta t. This should have been a small number. Okay. Yeah. Then that's fine. So so for cases where the accuracy condition does not impose any time step challenges, we can use this kind of a plotting condition that gives an upper limit for delta t, so that the random fluctuations of the process can be evident when you plot the data. Okay. This is more important, and this is more like an optional. This is more like an operational. We are not compromising any accuracy. This is only an operational requirement. So we have to keep this as an optional condition. If you okay, so when you write an algorithm, look at what is your A, B values are. Find out this accuracy condition. Establish this one first, and over and above, you may want to consider this also. Okay. Minimum of the two, yeah. But in this case, there is no minimum. In this case, there is yeah. In this case, this will give an infinite limit. That will give you the another. Yeah, you are right. So that could be the minimum of this. Yes. Now consider another process. Yeah, you take 10 power minus 1 or 10 power minus 2. It has to be a small number, 1/10 or 1/100th, something like that. It has to be much smaller than 1. That's it. So you may have a process like this where A is not constant anymore, A depends on X, and B is constant. Okay, so this is a typical of an OU process. So here what happens is, if you apply this condition for accuracy, so this term will give you infinity, okay, and this term will give you delta t has to be minimum of epsilon by k and infinity. Okay. So, dou a by dou x and modulus of that is this k. So, the first condition is giving epsilon by k, the other one is infinity because b is constant. So, the accuracy condition has to be given by this. Okay. And over and above, if you want this plotting condition, and you can take the minimum of either this or this. So, in this case also you can see that delta t, once you the beginning of the simulation itself, you can decide that this if you are going to go with this, okay, and this delta t is going to be constant. So, in step 2 you can fix your delta t and then loop only between step 3 and 4. Okay. Another process which is called a bistable process. This is, we did not discuss this in the class before, but it is interesting to see from the characteristic functions point of view. So, a of x is minus x 1 plus so here a is given as a polynomial in x. Okay. So, what happens is this process basically has a two stable state and it basically transits between the two. So, think about like there is a two metastable state for a particle and kind of shuttles between these two stable states. Actually, this also has an analytical solution, but because of its complex, I didn't discuss in the class. But if you were to simulate a Monte Carlo simulation of this process, you will see that the state starts in one state, one basin, and stays there for a while and then diffuses to the another state, remains there for some time and then comes back. And then when you continue, you will see many such transition from one state to another state and back and forth. Okay. So, that is a characteristic of this bistable process. So, in this case, so when you have cases like this, what will happen is you will see that the delta t is going to be minimum of since b is constant, so the other term is infinity, but this epsilon by dou a by dou x, the first derivative, when you take here, you are going to have something like epsilon by 3x square minus 0.4x minus 2.55. So, here you can see that the delta t depends on the current state value x. Okay. So, that is where sometimes you have to choose delta t adaptively during the course of the simulation. Okay. Depending upon the current x value, you will put this number here and then get delta t. Okay. And then at every time step you may want to update delta t. This is one way. Another way is to look at the possible range of x that you would have. Okay. Because you know that the simulation, I already said it's a bistable process, so I know what the ranges of x's are. So, you can set the entire limit of x, the entire limit of the state variable, and you can ask what is the range of this value is going to be in that range. Okay. Based on that, you can also choose the minimum delta t over that range. Okay. For example, in this case, suppose if I say x ranges from minus 3 to plus 3. Okay. I am just giving some example. So, you can actually put minus 3 here and get an estimate, and plus 3 and get an estimate, and then I think this derivative here, this goes between, I am just giving an example, 23.252 some 25.65. Okay. And then you can, since you know the range, you can take one of the maximum values and then decide your delta t upfront and don't change it anymore. Okay, so that will save a lot of your time, because if you include this adaptive time stepping in every loop, you are going to update your delta t, get the minimum maximum. There's going to be a lot of computational overheads that you don't want to do. So upfront you can decide what are my ranges, and then make sure you're always having a delta t small enough for the entire range of x values. Okay. It is something we do in differential equations. We call something called stiff differential equations. When we have, there are regions where your dynamics is very slow, there are other places where the dynamics is very fast. You cannot work with the same delta t every time, so you adaptively change delta t. Okay, so like that, here also we can change on the fly, or decide the range and then fix it accordingly. Okay. This is very interesting. I mean, you can do a lot of things here depending upon the process, but I'm just trying to outline the overall rule of thumbs that we follow in the numerical simulation of Markov process. Tomorrow we'll have class at 5 p.m. and bring your laptop. We can probably simulate few sample paths. I'll give some A and B functions for different Markov process, and you should be able to generate trajectories. Okay, because this is more useful from a practical point of view, because the analytical solutions are only available for very simple ideal case, and if you want to apply for your research or project, those are very limiting. But here, whatever complex functions you have, as soon as you identify what your characteristic functions are, then you have an algorithm to generate sample paths. Okay, provided that you have a computational resource to do that. So there is no limitation to what level of complexity you can approach here. Okay, so it's a very powerful method, and you can pretty much handle multivariables. Okay, here I talked about one variable. If you have a multivariate problem, you can still handle it. Okay, so it's a very powerful method. So we'll do this tutorial in the next class tomorrow.